Hello, welcome to Chapter 13, Section 2, where we are going to first start talking about angles of rotation. In this example, we're going to talk about angles in standard position. And before we start to do that, I want to kind of break into why we are going to do this. So I'm going to move this out of the way. I'll bring it back. I just got a blank sheet of paper here. This is what we know from the previous section. This is the SOHCAHTOA that we have been working with. So if I have a triangle, and it doesn't matter how I orient the triangle or what the triangle's orientation is, which means what position it is. If this is a right angle, and let's say that this is going to be the angle that I'm talking about, theta, okay? So relative to theta, this is the side opposite, this is the side adjacent, and this is the side, still the hypotenuse. And we know that the sine is the ratio of the opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. We know that. That was from the previous section. But there's one thing that got mentioned, but we didn't dwell on it too much. You see, if this angle is theta, then this angle right here has to be 90 degrees, subtract whatever theta is. That's because in a right triangle on a flat plane, the angles are going to add up to 180 degrees. This already takes care of 90 of those, so these two angles, whatever they are, both have to add up to the other 90. What that means is that both of them, theta and whatever 90 degrees subtract theta is, both of them have to be acute. Acute means less than 90 degrees. So this really starts to think about, well, can we find sine, cosine, tangent of right angles? What about obtuse angles? And what about angles that so far in geometry don't really make sense? What would that be? So in geometry, an angle can be acute, which means it's less than 90 degrees. It can be a right angle, and we usually use that little box to mark it. Or we can have an obtuse angle, which is more than 90 degrees. There's also something, and I always think it's kind of funny how we say it like a straight angle, which is a contradiction in terms. So we have basically two rays coming from the same endpoint, and they're going in exactly opposite directions, and we say that this is 180 degrees. But then what happens is, in geometry, if I keep opening it up, look at this, we don't really consider this as an angle. We actually say, well, the angle is actually this part, inside. Again, that's geometry. But what if I said, well, I do want to think about going from here to here? The important thing to notice about that is we're talking about motion. I said to go from here to here. What's happening as I'm pointing this direction, and then I turn, that's motion, and I turn, and now I'm pointing this direction. Well, what I did was I rotated. And the idea of rotation is what we're going to be talking about in this section. So all of the angles that we've talked about so far can be described in terms of rotation. I'm going to start here and I'm going to go there. I'm going to start here and I'm going to go there. I put the arrow to show which direction that I'm going. You can actually go the other way, that doesn't matter, but for consistency's sake, we're always going to go counterclockwise. And I think it's kind of funny, not funny, like if I show you, here's how I take time, okay? There you go, there's my iPhone. It's 11:29 when I recorded this. But I also have this clock I got for teaching 25 years, okay? And notice, you can see the second hand move, the other hands are moving too, and I need to set the time on this one because it's not the same as my phone, as you probably saw. But notice the direction that the hands are moving. They go in this direction. Well, that is clockwise. You're moving the direction in the hands of a clock. Counterclockwise goes the other direction. And the thing is that we agreed on what the direction was going to be before we connected it with clocks. That's why. So this 180 degrees, if I start here and go over here, and this one no longer know, I can start here, go past 180 degrees, and end up over here. These are called angles of rotation. We're thinking about movement, which is rotation. And you've actually been dealing with this before, because you know that there's 360 degrees in a circle. But what you never talked about was you can't have an angle of 360 degrees, so what are you talking about? And maybe your geometry teacher drew a picture with like 4 right angles, and maybe they drew something like this and said, well, that's 90, 90, 90, 90, 4 times 90 is 360. Maybe that's what they explained. But what we are forgetting is that when we say 360 degrees in a circle, we're talking about rotation. And again, like if you're talking sports, if you're talking about ice skating or dunking a basketball or snowboarding, if you say, yeah, you're going to do a 360, that means you're going to turn. There's that action verb again, turn. It's all about movement, rotation. You're going to turn through a complete rotation. So now we're going to connect that idea of movement to trigonometry. First, let's talk about the angles that we just had, but let's put them onto a coordinate plane and show them as being what we call standard position. So here are the guidelines for having a standard position. The angle has 2 rays. The 2 rays come together at a point called the vertex. The vertex of the angle is going to be, oh, should have said this, we're going to put the angle on a coordinate plane. Okay, that's all. So you got like the x-axis, you got the y-axis. That's what we're doing. In a moment, I'm going to use those. So we put the vertex at the origin, which has coordinates 0, 0, if you're not familiar with what the word origin means. One ray, which we call the initial side, is going to be along the positive x-axis. This means it goes to the right. So in both these pictures, the blue side represents the initial side, and that's going to be constant. The initial side is always going to start to the right, the positive part of the x-axis. The other ray is going to go off into the plane somewhere, and where it goes is the whole point. So that's what we're going to be looking at. Where did the other ray end up? So it could end up here in the first quadrant, second quadrant, third quadrant, fourth quadrant. As a matter of fact, we call these quadrants quadrant 1, quadrant 2, we use Roman numerals, quadrant 3, and this is quadrant 4. The reason why they were numbered that way is because we start with our angle of rotation, and as we go from 0 degrees to 90 degrees, we're in quadrant 1. If we keep rotating, we go through quadrant 2, then quadrant 3, and quadrant 4. I don't have, I really like to tell you evidence for things that I say, and I'll tell you, if I heard it in my own schooling or something, but I don't know if this is true, but I suspect that when we first started using graphs, or when we started using like simple graphs, we just used where it was positive. Okay, so like x is positive, y is positive, we can make a bar graph or a line graph or whatever it is. We've seen that. So I think that's why we start, and we call this quadrant 1, and that's probably why, but don't quote me on this. This would be a good thing for you to look up. That's probably why we start that way. We go through where x and y are positive first, and then we continue going all the way around. Now, think of it this way. Think if I had like a person, or if it, whoever, standing here, they would first be looking that way, and then we would have them rotate and turn to your left. So now you're looking this way, and then you keep turning, and now you're looking this way. You would have turned 135 degrees. But the question comes in, what if you turn the other direction? So if I had a person standing here at the origin again, the vertex of the angle, and this person, follow the arrow, turns to, remember he's standing on this, okay? So, or she or they are standing on this, they're going to turn to their right. In this case, negative rotation is clockwise. So this allows me to talk about negative angles, which makes no sense in geometry. If I said I want you to draw an angle of negative 45 degrees, that would not make sense at all. If you really knew what you're talking about, you would look at it and go, I can't do that. And you'd be right. So it's really important to understand that the angles we're talking about are angles of rotation. And rotation means that there's movement. You are turning. I'm going to keep emphasizing this. The angle of rotation represents a turn. Speaking of that, just a little aside, we often talk about, like, when are we ever going to use this? Think about all of the things in the universe that turn, whether it's a machine, just simply like wheels or gears, or if it's things that are natural, like the Earth or other planets that are turning. So what we're talking about is using a math description to describe the idea of turning. And we'll be getting into that. But first, let's do a couple of examples. So in order to do this, I made a couple of grids, but I don't want you to, we're going to estimate these angles, which is perfectly okay. So I think for the problems you're going to be seeing, it'll be like sketches. Okay, so I pulled this out just to show you what it is. This is a protractor, which allows me to measure angles. I am not going to use that, and you don't need to use one either. So don't email me and say, I need a protractor. You don't need to use one. All you're going to do is estimate it. We're going to do 3 of them here. The first one is 300 degrees. So I'm going to draw my initial side, and actually I'm going to do, let me show over here. I'm going to do what the example had. I'm going to switch with blue and red. So here's my blue initial side. My vertex is at the origin at 0, 0. Now, where is my terminal side at? Well, I need to rotate through 300 degrees. So I'm going to go 90 degrees. Another 90 degrees is going to take me to 180. Another 90 degrees is going to take me to 270. And 30 more degrees is going to take me to 300. So you don't have to write this. I'm doing this just while I explain. So I started out at 0. I went to 90. I went to 180. This is 270. 90 plus 90 plus 90. And then I'm going to go 30 more degrees, which is about right here. And again, notice that I did not use my protractor. Actually, let's just see how close I got here. I'll have it upside down. Oh, it should have been about right here. But that's okay. That's fine. It's the idea that matters. One thing you have to include is you have to include the direction. So I need to put an arrow at the end of my arc. It's not a full circle, so it's an arc. I put an arrow at the end of it, which tells the reader which direction that I went. Number 2, which is not numbered number 2, but that's okay. The angle is negative 150. Negative means, I'll draw my initial side right here. Negative means I'm going to go the other direction. So I'm going to start here and I'm going to rotate this way. That's now negative 90 degrees so far. And if I go all the way back to the x-axis, the negative part of the x-axis, I'm going to get to 180, negative 180. So I don't want to go that far. How much more do I need to include to get to negative 150? I need to go about this far. need to go about 60 more degrees. So this is going to be negative 150 degrees. I should have labeled this one too, 300 degrees. Finally, for the last one, 900 degrees. Now, the one thing you should notice right off the bat is that 900 is bigger than 360. So I'm going to start the same thing. I've got my initial side here that I drew in blue. Now, let's think about this. Each time I go past one of these parts of the axes, the upper y-axis, the left x-axis, the lower y-axis, the right y-axis, x-axis, excuse me, I'm going to go 360 degrees for the whole thing, but that means each time I'm going to go 90. So there's a couple ways I could kind of do this. And when we draw it, we kind of want to make sure that we do something so that it shows it. When you take the quiz, when you take the homework check, I'm going to tell you something because I wasn't able to like draw it that way for that, but it'll be okay. So what we do, just to make it obvious, is that we kind of spiral. So we make it a little wider. So I've done 90, 180, 270, 360. If I go another 90 degrees, now I'm at 450. Another 90 degrees, I'm at 540. Another 90 degrees, I'm at 630. And by the way, if you're wondering how I'm getting these, I'm just adding 90, 180, 270, 360, 450, 540, 630. Is that where I left off? Let's see, 360 and then 450. Okay, yep. So now the next one is going to be 720, bringing me one more time to 810, and then finishing up right here, put the arrow down at 900 degrees. So that means that the other ray is going to go this direction. Now, one thing I want you to notice is 900 degrees actually is represented by the spiral. That's really important. Each time, it's the arc or the spiral that tells me which way that I'm going. Remember, one more time, it's always about the motion. It's always about the turning. But in the next video, we're going to talk about the fact that how many times do I turn until I land at that same place? In this case, this looks like the same picture without the spiral if I had just done 180 degrees or negative 180 degrees. We'll get to that in the next video.